In ROADART, a novel diversity engine tailor-made for track-to-track and track-to-infrastructure communications was developed. As a concept, diversity is a condition of having or being composed of different elements or qualities. In communications, it is a method for improving the reliability of signal reception with the use of uncorrelated channels that experience different levels of fading and interference. In ROADART, antenna or space diversity was used as the base of the diversity engine. More specifically, the maximum ratio combining scheme was implemented in the communication unit using 4 RF chains. On top of antenna diversity, a beam pattern selection scheme was implemented with the use of reconfigurable antennas. One of the available patterns is omnidirectional for broadcast, multicast transmission or reception. The rest patterns are directive and can improve performance for several applications like CSCC and platooning. Therefore, the developed and demonstrated ROADART diversity scheme is a hybrid space and beam space diversity scheme with the use of ESPAR antennas. 2 antennas were placed into the side mirror casing. The outer antenna produces either omnidirectional or directive patterns looking in front or back with respect to the track axis. The antenna at the inner side produces either omnidirectional or patterns looking in or looking out of the track. With 4 antennas and 3 patterns per antenna, 8-to-1 pattern combinations are possible. In ROADART, 7 modes of operations were implemented: static, without pattern reconfiguration, random pattern selection, random selection with omni support, a geo-tracking geo-networking beam selection, a dynamic reconfiguration scheme for the outer antennas only, a dynamic scheme with omni support, and a full dynamic reconfiguration scheme for all antennas. In order to monitor, validate, and evaluate the performance of the diversity engine, several key performance indicators were measured or calculated in real time during tests and demonstration. The KPIs were displayed in real time using the visualization web tool Grafana. More specifically, signal-to-noise ratio for ROADART versus conventional V2V transmission, achievable throughput in the available wireless channel, bit error rates where visible peaks indicate failures of the conventional scheme, latency in the leak level measured in the physical layer, the SNR improvement due to the ROADART platform, the packet error rate, and the coverage probability that determines the link availability. One of the developed and demonstrated diversity operation modes is the geo-tracking geo-networking scheme. According to this mode, the patterns are selected based on the relative geometry of vehicles in a given time instance. Through the ROADART localization engine, each vehicle is aware of its position. Moreover, through the received ITS messages, each track is able to know the position of the cooperating vehicle. The engine calculates the relative heading angle between the vehicles, and each vehicle decides on the combination of patterns that best fits the relative geometry of the vehicles. The specific mode can easily be demonstrated in an overtake scenario. In this example, an overtaking maneuver is taking place inside the MN test track. It can be seen that as the following vehicle overtakes the preceding vehicle, the patterns gradually change from looking front to looking right and then to looking back, tracking the cooperating vehicle. A corresponding pattern reconfiguration takes place to the other vehicle. The geo-tracking algorithm does not provide an optimum solution as far as the radio-related KPIs are concerned, since the radio channel behaves as a random variable with fast fluctuations. However, the geo-tracking algorithm provides significant improvement in the long term with minimum complexity, since the algorithm extracts the patterns through simple geometrical calculations. This video sample presents the behavior of the algorithm during an overtake maneuver that took place in the A55 highway during the ROADART demo. In order to track radio channel fluctuations, 3 dynamic reconfiguration modes were developed, either with omni support from 1 RF chain per mirror, or with full reconfiguration of all antennas. The engine monitors the SNR and reconfigures the patterns when it falls below a predefined threshold. Reconfiguration is performed in 2 stages to ensure compatibility with the radio standard. The dynamic reconfiguration schemes were presented, tested and evaluated during the ROADART demonstration event. Throughout the ROADART demonstration event, the transceiver operation was monitored in real time with the use of the Grafana tool, where functional and performance metrics were continuously recorded. Explanation of the presented metrics and quantities was provided to the attendees. In addition, real-time evaluation was performed with KPIs comparing the ROADART diversity engine with conventional communication schemes.